Staying with clusters, our next speaker is Matteo Bianchi, who's going to talk about, did I screw your name?
No.
How should I have said it?
Bianconi.
Bianconi, sorry, thank you very much. No, good to correct me. I was going to talk about pre-processing in massive galaxy clusters at a redshift of 0.2.
Thank you very much for the introduction, and thank you very much for letting me present some of the recent results from the survey LoCuSS, in particular on star formation quenching from this sample of rather local galaxy cluster we have in the survey indeed. I'm from Birmingham, and part of the team is listed here, some in Birmingham, some scattered around the world. So as we, this is a specialist meeting on indeed quenching in galaxies, so I won't again reiterate over what we're trying to understand, but graphically what we want to describe is how such an object can be transformed into that one. So how active blue spirally sort of shaped, call it whatever you like, gets transformed into something that is the polar opposite of it. And in particular, if what I'm trying to do at least is to try to show if environment has a play in this transformation, and if there are different ways of sort of obtaining the same results according to how these objects get accreted into clusters in particular. And LoCuSS is a rather ideal tool for this, given that it targets the most massive and most luminous X-ray clusters at rather local redshift. We are talking about 50 in this case. And it's ideal LoCuSS in the sense that it includes a very extensive coverage, both in terms of wavelength. So we have from X-ray all the way down to far infrared, together with also optical spectroscopy, but also in terms of coverage, in terms of area covered by this instrument. And so we see here an example for Abell 1835. We see here the cluster core, and we see that all the footprints of the different instruments sample well outside of the virial radius of the clusters. And so we're really sampling the first instances of accretion of objects into the cluster potential. So really sampling if there is anything happening to them as they are accreted onto the cluster. Just to give you some quantities, for both passive and active sort of family of galaxies, we are kind of complete down to this stellar mass. For star-forming objects, we go an order of magnitude deeper, obviously because they're more luminous. Again, very nice completeness in infrared, crucial for sampling star formation. And as I said, and as you can see here, very nice coverage also in terms of optical spectroscopy, which is crucial for the selection of cluster members. But also, it's crucial for the detection of exciting new sample of objects. So optical spectroscopy combined with X-ray imaging allowed us to discover about 100 new group members in the surrounding of our galaxy clusters, but also in the background and in the foreground. And so we see that the furthest from us is at a redshift of 0.7, but we do have 35 around the cluster that we consider, and you can see them here. And the fact that they again, for Abell 1835, where we see 4 galaxy groups in its surroundings, the fact that they still emit in X-ray is a good hint for us that these groups are at the first encounter with the cluster potential, otherwise they would get stripped of their hot gas and so they would not emit. So that information combined to where they are located in the classical phase space diagram, where we have cluster centric distance with respect to peculiar velocity of this galaxy with respect to the cluster. Sort of these groups here shown as magenta circles are located preferentially around where recent inflows should be. And so again, we are quite safe in saying that these groups are just experiencing the cluster potential for the first time. Obviously, we don't see any in the cluster core because they get outshined by the brightness of the cluster itself. And swiftly moving to what we see when we focus on the fraction of star-forming objects selected accordingly. In this different environment, this is what we get. Again, keep in mind on the x-axis we have cluster-centric distance and fraction of star-forming objects on the y-axis. We see a couple of different interesting things. We see a coeval in a value for sort of reference values for us is a sample of Higgs galaxies selected in close proximity redshift space, at least, of our clusters. And so we keep this as a reference. And we see that the fraction of star-forming objects for clusters never really reaches that value, even at rather high distances from the cluster itself, which is well above, well outside of the cluster virial radius. And so this tells us that something is happening to galaxies in cluster prior to their, to galaxy prior to their arrival into the cluster potential. To explain that, we can simply, using semi-analytical models and numerical simulations, obtain this relation by assuming that once the galaxies are into the cluster, a sort of a slow quenching process affects star formation. We're talking above 1 gig a year, maybe 2 even. But more importantly, once again, we need this process to start earlier than its actual arrival or its pass through the virial radius. And so the necessity of pre-processing, and so environmental effects, so, as you want to call it, already occurring prior to the inflow of these objects into the cluster potential. And crucially also, what we see for group is quite striking. We see that they very much look like the cluster cores. And so nothing happens to the fraction, almost, to the fraction of star-forming objects in groups, even when they enter the cluster environment. And so what this seems to tell us is that groups are actually populating, or these massive groups are actually populating clusters with very old, passive, and massive objects. And nothing is happening to them, more or less, even when they actually enter the cluster. Similarly, if we put this into perspective of the overall mass growth of these clusters, we can, below this redshift, we can measure, again, from simulations that clusters grow about 32% in mass, so quite a substantial increase at local redshift. Half of it is due to massive halos, call it groups of different sizes, and half is due to inflow of individual halos. And once again, we can see quite neatly here, very simply, the cluster population of star-forming objects indeed seems to be halfway composed of objects that are infalling on their own from the field, and objects that are infalling instead in groups. In order to study in particular one of the more interesting objects that we have in our sample, Abell 1758, very famous cluster for being particularly complex in its dynamics, again, we focus further on this object as a case study to see whether the cluster dynamical status has an impact on the star formation of its members. And we can see here once again the power of the LoCuSS survey we see through different probes. Again, the complex structure of this cluster we see. The cluster itself is divided into main subclusters, north and south, which are further subdivided into two, especially north, maybe in the south. In X-ray and definitely in weak lengths in two. We see where one of our newly discovered group is. And we see also that we are able to see direct evidences of ground pressure stripping, and also, again, a very active object, still in its accretion phase. And we focus mostly, due, again, to the extent of our wavelength, on dust mass, to see if there is anything interesting there. And here, simply, we plot star formation rate with respect to stellar mass, dust mass for cluster and field star-forming objects. Again, field drawn from our own sample of galaxies. And we see that, well, dust mass doesn't seem to change much. But again, we see a systematic decrease or shift towards lower value star formation rate when it comes to cluster galaxies. And again, if we apply a simple exponential decrease, we can put a number to the quenching time scale if it follows this simple relation. And again, we find 1.2, 1.5 gigahertz, so again, slowish process. Another view of Abell 1758 is shown here. We have a slice in declination and redshift, where we see, again, all the dots are our confirmed members, nicely separated in redshift space according to their belonging to, say, for instance, the south clump and the north clump. And here we see also the group members. And what we do here is plot the dust to stellar mass ratio, which is nothing more than the fraction of dust mass with respect to stellar mass. And we see, first of all, that in the cluster cores, there is hardly any dust. So again, color codes the amount of dust, if you will, rather more dust. There is hardly any, not surprising, we know that. Cluster cores are quite boring. There's not much going on. We see, though, an increase of these dusty objects the more we go towards the outskirts. And interestingly, groups sort of sit halfway, which is actually more clearly shown in this one-dimensional plot, where again we see just the radial trend for from just simply counting for the north and south column. And we see that, well, the scatter is rather enormous, but around the group region, and again here I'm just plotting the star-forming or dusty fraction of objects, there is a dip. So potentially, again, something is happening or happened already, even to dust in group members. Again, we're just studying one case just to test the method. But again, the power of LoCuSS is that we have 30 of these groups, and so stay tuned for more results. What we can see already, though, if we plot simply like a mean of the spectral energy distribution of field and cluster galaxies, we see a substantial decrease at sort of like 100 micron, which is supposed to be related to small dust grains in around birth clouds of stars. And so definitely something is happening in this regime. Now, whether as some theoretical paper, whether this is related to sputtering, for instance, destruction of this dust grain because of the intense radiation that these grains are experiencing once they enter the cluster core, once they enter the cluster environment due to the intracluster medium, or is this just reflecting a decrease of the overall star formation rate because, as we saw before, other mechanisms reducing star formation rate, and what we see here is just less luminosity being shown around. It's still a matter of debate, but even for one cluster, and even for it being very complex, we see this quite clear signature. And so I leave you with my conclusion. Again, the uniqueness of LoCuSS is that it contains so many different environments all at once, and it's very easy and very controlled to select different sort of objects. We seem to find univocously at these redshifts star formation quenching being slow, and potential hints of effects already at these redshifts of dust consumption or destruction. And crucially, the importance of group in both the population of clusters but also mass growth. So thank you again for your attention.
Thank you. That was great. Questions? Let's go Becky, then Tim.
Hi, thank you. Great talk. So your plot of the radius in the cluster against the fraction of galaxies that you showed, where you were saying that the pre-processing was happening, you had on one side at the sort of like far end of the sort of just entering the cluster, you had sort of say 6 gig years ago and then like 1 gig a year close in. And I'm sorry if I missed it, but I was just wondering where those timescales came from.
Right, yeah, that's just a reflection of different timescale attached to a semi-analytical model on top of that was attached to the accretion history of halos into a cluster. So we took the 75 most massive clusters in Millennium simulation and attached semi-analytical models of star formation quenching, that exponential. And so we just, applied different time delays for it. And we saw that it cannot be that long. So it doesn't, this is just a simplified version for, so you would see this fraction, say, curving just at the very end, if the timescale would be like that. Whereas this sort of trend is more compatible with 1 gig a year.
Right, I see. So, sorry, you're not saying that it's taking 5 gig years to get
no.
there.
So,
the shading, sorry, right, that's what I didn't
no. So,
right.
Cool. Tim, reasonably quickly.
So, your 1 to 2 gig a year timescales are very similar to the depletion time of molecular gas if you just leave it alone. So does that mean you think that this is more strangulation than an active quenching?
Well, I wish I could have the answer. So, is it though? Isn't it? Well, we definitely cannot. So we don't have the resolution to see necessarily exactly all the different phases of it. It is. Well, I would not claim that run pressure stripping doesn't do anything to it. Personally, this is my first adventure into longer wavelengths. So when it comes to, say, for instance, stripping of more dense clouds, I'm relying on somebody else's work. I guess everyone agrees that run pressure is very, very effective when it comes to like more diffuse phases. Nevertheless, I'm sure I've seen some plots here and there showing that even the denser clumps can be extracted from the cores of galaxies and so on. In this case, I have to say that the majority, or at least, so the one of few things that we can say from morphology, we do have some HST images. We don't see incredible disruption in the morphology, and so strangulation is definitely could be in for sure, more than actual merging, or at least if it happened a long time ago. So.
Excellent. Lots more to discuss over lunch, I think. Let's thank Matteo again.